Today we're going to take our knowledge of adding vectors and we're going to apply it to some problems. Now you saw these type of problems already in grade 11. We're just sort of going to ramp up the difficulty level a little bit. Okay? Yes, Tarzan and Tarzana. They are brawny ape people. Or so it says on page 95. Now I don't know what that really means, whether it means that they are raised by apes. What does the fact that they're brawny or not have to do with anything? I don't know. It's always very confusing, I find. So it says here on page 95, Tarzan and Tarzana are brawny ape people. They decide to race across the river. Both are excellent swimmers and have the same ability. In other words, they can both swim at the same rate. That's what that means. Tarzan swims straight across, landing on shore directly across from where he started. Tarzana jumps in and points herself across the river, but ends up farther downstream, where she reaches the other side. The two are pictured in figure 324. So you see that Tarzan, he decides that he wants to end up straight across, so he sort of goes upstream a little bit and ends up straight across. She decides she's just going to go straight across, and the river takes her downstream a little bit. And then the third one, who finished first, says, then there was Cheetah, faithful, brawny ape pet.
What?
Yeah, exactly. First of all,
why wouldn't they just simple as be like John?
Or just the cheetah thing. He's just a monkey, right?
Cheetah is a monkey?
Yeah, and what's with that?
Cheetah.
No, cheetah's a monkey.
Why is a cheetah a cheetah?
I don't know.
Why did you name a monkey cheetah?
I didn't name them.
Why did they name them?
Because they're ape people. They're raised by apes. They have.
You're scared of cheetahs. Have you ever seen them?
Maybe I'm scared. Yeah, that's a leopard.
Yeah, a leopard.
Oh, it's a leopard?
Oh.
Well, then clearly cheetah has the wrong name. Why wouldn't they just call him monkey? And did you know, and while we're talking about those kind of things, did you notice when you were a kid, you ever watch Franklin the Turtle?
Yeah.
How come Franklin was the only one with a real name?
And the other ones are called like
The other one was just bear, raccoon, you know.
They just have a bear.
Like, what's so special about Franklin?
Because there were so many turtles in the show that they didn't want people to get
Oh, I guess, yeah.
Then there's like Mr. Bear and Black Bear. Oh.
All right, so Cheetah, he chose to swim across the same river, but at a time when the floods were raging and the river flowed at 5 times the velocity it did when Tarzan and Tarzana swam.
He's flowing during a flood, a raging.
Not very smart. Well, he's an ape, right?
No, he's cheetah.
No, he's an ape.
Why is he? I'm so confused. Oh.
All right.
Did his parents teach him any better, Tarzan?
No. He was raised by monkeys.
He's not going to take it across. He's going to die.
Is he raised by monkeys or he's actually a monkey?
He's a cheetah.
Why would monkeys raise cheetahs?
Why would a cheetah raise a monkey?
Because they're smart like humans. Maybe they're going to like use them to fly. Cheetahs are so fast.
All good questions.
Yeah,
You'll find lots of weird things in this textbook. It's a lot of fun actually.
Okay.
Okay, so relative motion. In trying to answer the posed problem, we need to define what relative motion is. Suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road as shown in figure 325A. If you flip the page over, okay, and I'm just going to go back a page here. I'm going to try and draw this. Okay, if you see, now on page 96, okay, if you see the patrolman there, he's at rest, right? You're foolishly traveling at 140 kilometers an hour, so he registers 140, right? But if the policeman is driving at 100 and you're driving at 140, then his radar is only going to pick up 40 relative velocity. So you were traveling 40 kilometers an hour relative to him, right? As if you were stopped, you'd be only traveling 40. So it's the difference between the two.
Oh,
okay.
That's why they're always stopped in the radar.
You just use the relative.
Well, you could. But he would have to have his. Yeah. Okay, guys. Not. Yeah. Okay. The patrolman will measure your velocity relative to his position. In this case, the patrolman is not moving. Let's assume the velocity he measures is 140. Your velocity is said to be 140 kilometers east, measured relative to the ground. Now, suppose you pass the patrol car with a velocity of 140 while it is moving with a velocity of 100 kilometers an hour in the same direction. This time, the velocity measured is 40 kilometers an hour relative to the patrol car. While the patrol car has a velocity of 0 in its own reference frame, its 100 kilometer an hour velocity must be measured relative to the ground, as in figure 325b. Notice that your velocity is the same, but the two measurements done by the patrolman are different. The bottom line is that a velocity value is measured relative to a reference frame, which we did talk about in grade 11. In everyday use, we are accustomed to using the ground as a stationary reference frame. This frame is implied in most problem situations. Flip the page over. Now, what if, they don't ask it here, but they should, what if that patrolman is traveling 100 kilometers an hour in the opposite direction?
240.
If he's going like this,
West?
the car, the patrolman's going like this at 100, and you're driving like this at 140, what's his radar going to show? 240? Right, you are. Okay, 240. Very good. Okay. So now we can apply this knowledge to the swimmer in the river. I'm reading on page 96. If Tarzana floats with the current, it will appear to her that she is not moving relative to the water. To actually measure her velocity, someone must stand on shore relative to the ground and watch her go by. In fact, to measure the river's velocity, we must also measure it relative to the shore or relative to the ground. In order to keep these velocities distinct, we use a series of extremely confusing subscripts. Okay, on page 96. Now, it doesn't actually say extremely confusing. That's my own little editorial comment. But you'll notice here that it says VOG is the velocity of the person or object relative to the ground. VMG is the velocity of the medium the person or object is in relative to the ground. And VOM is the velocity of the person or object relative to the medium it is in. This velocity is not readily observed because it is affected by the medium's velocity. It could be considered the person's or object's ability without influence, such as swimming in water with no current. You can come up with your own subscripts. We will. Choose symbols that you'll find easy to remember. We will. In fact, you might even have someone have done it inside your book there. Has anyone got markings inside the book?
Equal B plus C.
Yeah, some other stuff? Okay, so, and if you want, you can do this right in your book, because I've got beside VOG, what I'm really talking about is VR, or simply resultant. The resultant velocity is the velocity of the person or object relative to the ground. It's the overall, what you see. It's the resultant. They made it far, far too confusing in my mind. VMG is the velocity of the medium the person or object is in relative to the ground. The velocity of the medium. In other words, the current or the wind speed. Okay, you're only going to see rivers, you're only going to see wind. So that second one should be VC or VW, which I usually call wind, or simply C and W. Current and wind. Current and wind. Obviously, if it's a boat or a swimmer, it's not in the wind. Right? And then the last one, VOM, is the velocity of the person or object relative to the medium in it. In other words, how fast are they actually swimming? How fast would they be swimming if there was no current? How fast would the plane be going if there was no wind? Okay? Now, depending on whether it's a plane or a bird or whatever, I usually would call it VP for plane, or V boat if it's a boat. Okay? So it's equal to the plane speed, the boat speed, and so on. I find these much easier than the ones that they've talked about. And the relationship between the three quantities is, and I've shown you this in grade 11 too, right? The resultant is equal to, if we're talking about boats, the boat plus the current, right? The overall resultant is the boat speed plus the current speed, add them together. The overall resultant is, yeah, the plane plus the wind.
When you say it's only a plane, what car?
Well, it could be a car, right? I mean, generally, right? I mean, we could say in this case the resultant is Tarzan plus current, right?
What about Tarzana? What would you put her then? If T is Tarzan?
I don't know.
What if you had two of them? What if you
What about Cheetah? Because there's already a steep current.
I don't know, man. See? They should not have named him Cheetah.
They
What?
should have named him Monkey, and they should have named her, I don't know, but something clever. Not with T.
What about if it's a sailboat that needs current and wind too?
Oh, good question.
What?
He's asking what if there's a sailboat and it's current plus wind. Well, then I guess it would be,
Adding up.
yeah, just add them all, right?
So you just add those?
Yeah, I mean, the resultant is simply add up all the vectors. That's a great question. Resultant would be if it's a sailboat, right? So it'd be the sailboat speed itself, which really would be nothing, right? Because sailboats don't have their own power.
What if you roll?
Sailboat plus wind plus current. Now, actually, correct me if I'm wrong, I don't know much about sailing, but doesn't, like, if the wind goes this way, the boat still goes that way, right?
Yeah.
Like there's some sort of, yeah. So
But if you're trying to go one way and you have the sails out and you're trying to go like the wind.
we will ignore sailboats in rivers on windy days.
You will?
Yes.
Okay, good.
All right, let's go to example number 7. Example number 7 on page 97. In one dimension, the river problem has 3 possible cases shown in figure 326. Now, this is incredibly simple. When the river flows, its velocity is 1 meter per second east. Tarzana can swim at 2 meters per second in still water. So case number 1, there is no current. Case number 1, there is no current. So she can swim at 2 meters per second in still water. So what's the, if she swims at 2 meters per second, then what's the resultant?
Hey, isn't there 1 meter per second east?
Yeah, but there, in case 1, there's no current. The river's.
Yeah, we don't have that.
It's in your textbook.
Oh, you don't have it on your sheet?
No,
Oh, really?
Example 7, then example
Oh, I need to make a new sheet, I guess.
5.
Okay.
So just write in case 1.
Sure, right. Case 1, no current. Resultant is 2, obviously, right? I mean, it's so simple that it's not even worth writing down. If she's swimming with the current in case 2, it's east, right? She's swimming at 2. The river is going at 1, giving us an overall resultant equal to 3. Like, not rocket science at all here, right?
Well, that's pretty tough.
Yeah. And obviously, and they made it way too complicated with all those subscripts and stuff. Case number 3, if she's going against the current, right? 2 meters per second, 1 meter per second, giving us an overall resultant of 1. Not too earth-shattering. Okay, and they take a whole page to do all that.
They suck.
Yeah.
Like, can you just like,
They also named monkey cheetah.
Yeah. All right, you guys have example 8? So reading on page 99, we've learned that when we use vector equations in 2 dimensions, values cannot be substituted in the equation directly. This is because vector quantities are no longer collinear. In other words, we have to add them tip to tail. Now the pictures there at the top of page 99, they show the resultant. Which one of those 3 vectors is the resultant? There's 2 solid red ones, and then there's like a
2 double line?
double line red one. Which one is the result?
Other double line?
The double line, exactly. Okay. So we're just going to skip right to example 8. Assume that Tarzan can swim 2 meters per second. The current is 1 meter per second east, and Tarzan is seen to swim directly across. He is seen to swim directly across. In other words, someone on shore sees him going straight across. Now, is that his resultant velocity?
No.
He ends up straight across to where he started. That's his result. So what did he have to do? He had to go, remember the current's going to the right, right? So he had to swim like this. This is Tarzan. The current is like this, and he is seen to swim directly across. So that is the resultant. So Tarzan plus current. Now it is a 90-degree angle. Now you got to be careful here because we've already said on the previous page, was it the previous page? Yeah, right? Resultant is Tarzan plus current, but in this particular situation, that's still true. The resultant is the Tarzan vector plus the current vector, but because it's a right triangle, it's actually going to be t squared equals c squared plus r squared. Okay, so that's different. We can say that the resultant is Tarzan's vector plus the current vector, but geometrically, mathematically, t squared is r squared plus c squared. So just a little cautionary note there. Okay, so there'll be 2 questions. What is the resultant? Okay. Now you'll notice here that I put the little vector signs on top. Here I did not. When you don't put the vector sign on top, that means the numerical value of t without the direction. Okay, that's what that means. So in other words, just 2. So we're t here is actually 2. The resultant is what we solve for. The current is 1. So r is going to be the square root of 4 minus 1, square root of 3, right? .73. So he actually tried to swim at 2 meters per second, but only ended up going 1.73. Okay. What direction did he have to go to end up at that? What direction did he have to go to end up at that? So that's going to be opposite over adjacent. I guess I probably should go sine because I like to use ones I know, but we'll use tan, I guess. So opposite is my C, my adjacent is my R, 1.73. So that's 1 divided by 1.73 is, oh, and then the second tan of that, I get 30 degrees. That would be north 30 west, wouldn't it?
How come it's not west?
Because the north is the one that's west is over here, right? So the first one is the one that is straight one direction. It's not at an angle, right? North 30 west. Or you could say 30 degrees west of north,
Do
too.
we always find what the result is, not what, we wouldn't do the angle towards that, because we're.
That's what I did. This is the angle that he has to, this is not the resultant angle. This is the angle that he has to go straight across.
Oh, okay. Yeah,
Right?
if it was west, north, we can just go.
Yeah. Okay. Now, Tarzana, she decides she's not going to fight the current. She's just going to swim straight across. I don't know. Is she? She swims straight across. The current pushes her downriver. What is her result? Will she go faster? Current. Now, in this case, once again, resultant is equal to, we'll use T for Tarzana. Yeah, I know. Should have called her. Yeah, that'll go over real well, Zach. That was Zach Watson with that comment.
Pause.
So in this case here, we've got r squared is equal to t squared plus c squared. So that's going to be 2 squared plus 1 squared. Oh yeah, this is going to be way more, isn't it?
Yeah.
It's going to be, in fact, 4 plus 1 is going to be the square root of 5, isn't it? 2.24. She goes quite a bit faster, doesn't she? Does she get there first? She does have to travel a further distance, doesn't she? He only goes straight across. She has to go farther, but fortunately she's going faster. At what speed, at what angle does she end up going? Would it be 30 as well? Gut instinct tells you that it should be, or at least mine does. Would it? Opposite over adjacent, so that's going to be 1 over, oh, hang on, my adjacent is not. My adjacent is 2, is it not? 1 over 2. It can't possibly be the same number, can it? 26.6. North, 27 east. It's not the same triangle. It's not the same triangle. Okay. We'll get to finding the time to cross first right away. Now, if you're in the book, we're on the bottom of page 100. We're looking at cheetah now.
No, not cheetah.
Monkey. He swims at 2 meters per second. Current is 5 meters per second east. Cheetah swims like Tarzana, pointing directly north. So he goes like this. I don't know why I draw it so big. I'll put Should I put M for monkey?
Yeah.
Just to not to confuse things.
Then there's current.
Current is much bigger this time. Yeah. Cheetah, you stupid monkey. What are you doing swimming in the river? Didn't I teach you anything when you were a little monkey? I don't think monkeys swim, do they?
The Bennett scale.
The Bennett scale.
Last year. That one was a 5 on the Bennett scale.
It's good to know. Resultant is monkey plus current. Monkey swims 2. Oh, hang on. Now, in this case here, I'm going to write r squared equals m squared plus c squared. So the resultant squared is going to be monkey 2 squared plus 5 squared. That's going to be 4 plus 25, square root of 29.
Monkey's going very fast.
5.4 meters per second. And clearly, he's going to end up much farther downstream, right?
Yes.
Would it be 5 times farther downstream, do you think? We didn't actually figure out how far downstream she went.
No.
So this is going to be tan minus 1. Opposite over adjacent. That's going to be 5 over 2. Second function tan of 2.5. 68 degrees. That's going to be north, 68 east. All right, but what about the time to cross? Top of page 101. In all 3 cases, the diagrams could have been constructed by setting a scale using givens and connecting them in the manner dictated by the vector equation. The final answers could have been obtained by measuring. Who's going to do that? So who finishes first in the race? To find out, we need to look at the 3 vector diagrams which are shown together in figure 3.3.5. The equation b equals d over t rearranged to become time becomes t equals d over v. We now need to find out which v to use. If you look at the diagrams in figure 3.3.5, the velocity vector that points in the direction of the desired motion, north in our case, is the appropriate choice. The other vectors involve the motion of the current, which does nothing to help anyone cross to the other side. Tarzan swims at 1.7 in the north direction. Notice that for Tarzana and Cheetah, the velocity directed north is 2 meters per second. Thus, Tarzan finishes last. With Tarzana and Cheetah tied for first. They both get there at the same time. Because their speed in the direction that they need to go is both equal to 2. The lesson of this story is that if you wish to cross the river quickly, direct all your energies to do so. Tarzan used up some of his velocity in fighting the current in order to end up in a position directly across the river. Right? So if you happen to find yourself being chased by wild monkeys in the forest, right? Or cheetahs, and all you really want to do is get across the river, don't bother swimming upstream, swim straight across. But if you care about where you're going to end up, then obviously you have to. Yeah, exactly. Okay, so I think you guys have one more question there. It's in the book, but let's just see here. You guys want to give this a try, like with a partner kind of thing? See how you do? I'll give you a bit of a hint here. A pilot with a heading of north 30 east and an airspeed of 400 kilometers an hour flies into a wind coming from the north at 110 kilometers an hour. What is the plane's velocity relative to the ground? In other words, the resultant. So this is the plane speed. When they say airspeed, that means the plane speed. What is the plane's velocity relative to the ground, and how long would it take to complete a journey of 1,000 kilometers an hour at north 30 east? Now you will notice, well, hang on. I'll let you discover that problem. Let's have a look at this with components here. So a pilot with a heading of north 30 east and an airspeed of 400 flies into a wind coming from the north. What is the plane's velocity relative to the ground? How long would it take to complete a journey of 1,000 kilometers at north 30 east? Okay, so once again, the resultant is the plane plus the wind. So we're going to find the individual components of the plane and the wind, and we're going to add them together. So we've got north 30 east. North 30 east is like this, right? So this is our plane. This is our PY. This is our PX, right? This is 30 degrees. So PX is opposite. So that's going to be, because I'm doing it by components.
Why?
Because components are our friends. Remember from yesterday how easy it was?
When we don't do the other way.
Because is it going to be a right triangle?
It is, yeah.
It is?
Yeah.
How do we know it's a right triangle?
No, it is now, that one you just do.
Yeah, but like, isn't it going to be something like this?
Yeah.
So you can't use Pythagoras, can you? Right? You got to do it by components. So that's why I showed it to you yesterday, the components. So PX is opposite, so that's going to be 400 sine 30. Airspeed is 400, right? 400 times the sine of 30, 200. I'm going to put the y over here. This is going to be 400 cos 30. Mm, 346.4. Both positive, right? Brighten up. Now the wind is straight south, isn't it? So that means that, not S, that means that the wind X is 0, and the wind Y is simply minus 110. So,
PY are horizontal components, right?
say again?
PX and PY are.
Yep, X and Y components of the plane. So the Rx is going to be 200 minus 0, sorry, plus 0. And the Ry is going to be 346.4 minus 110. It's really adding plus 110. 236.4.
How do we know when to do a component?
Always, do everything by components now.
What?
Do everything by components.
We were before, we cheated,
Yeah, you're right.
why weren't we?
Because we knew it was an automatic right angle, I guess. Good point. Yeah. Because it had to be a right angle.
And that's the only time we kind of skip the component. part,
Yeah,
which is
pretty
right.
much. And you could do it by components. You would get halfway into it and realize, oh, hey, I don't need to do this, right? Because, yeah, I guess we could have done the one by components probably. Anyways, so I'm going to redraw this. So I've got 200, 236.4. There's my resultant. R squared is going to be 200 squared plus 236.4 squared. I get 309.6 from 0.7, I guess, if we round that up properly. 309.7 kilometers per hour, but at this direction, right? Are we traveling at north 30, what was it?
No, we're in north.
North 30 east? No, we're going to be going this direction right here, which is going to be something completely different. It's going to be 236.4 over 200. Make sure your calculator's in degrees, of course. 49.7, we'll just go right to 50. That's going to be east 50 north. So in fact, here's a great example where the textbook's got a mistake in it, because the question asked, how long will it take to complete a journey of 1,000 kilometers an hour at north 30 east? It's going to take a long time, because guess what? They're not going that direction. Right? Should they have given you the direction in that last question of how long it would take? It shouldn't have given you the, it should have just said, how long will it take to complete a journey of 1,000 kilometers? Because you're not going at east, or north 30 east, you're going at east 50 north.
It is stupid, but.
Yeah, it's a little bit stupid.
Yeah,
But if you had to figure out the time, it would simply be V bar equals D over T, right? So this would be 309.7. Put the 1,000 kilometers up there. T equals.
Yeah, maybe put it now.
3.2 hours. Which is what I think they actually get. Yeah, they might, yeah. But they don't say anything about the angle, right?
East of the north.
Okay, so that's good. Blah, 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 blah. There's some problems in the book here that you should probably look at on page 116. Do I have a note at the bottom of your page which questions to do? No? Okay, so there's some relative velocity questions on page 116. And basically, we're done the unit, you guys.
No.
So you should do, starting with 35 to 43, maybe. For sure, you need to do number 36. Okay. On Tuesday, we'll take a brief look at vector subtraction, because we need to remember how to do that. Can we go Wednesday for a test or no?
Yeah.
Thursday?
Yeah. Let's go to Thursday, we'll do Wednesday.
Thursday?
What's the date?
I'm not sure. We'll go with Thursday.